How is everyone? Doing good. Awesome. Thank you. I didn't play the music that goes with it. Alright, so we'll talk about SLPs tomorrow in 222, but just generally let me say really nice job everybody on SLP presentations today. So I did not get to listen to many of them because I was in the main room, but almost everybody showed up, and from feedback I've gotten, it sounds like lots of interesting presentations, lots of good work there, so really nicely done. All right, so your homework is turned in, presumably, and I will get that graded in the next couple of days, and we'll talk about the homework on Wednesday. Any urgent questions on the homework before then? All right, righteous. So let's continue talking about languages. Yeah, I made those questions. I don't think there's a graph theory section in the book, or else I didn't like their questions, so I just put those together. All right, so we were talking about phrase structure grammars last week, and we were doing analysis of phrase structure grammars. So we're starting with a grammar, G, and we were analyzing it and figuring out what strings belong to that that grammar. So remember, a phrase structure grammar is a vocabulary, which is a set of symbols, a subset of that, which are the terminal symbols, a start symbol, which is an element of that, and then a set of production rules. And those production rules basically let us transform one set of symbols into another. And the idea is you start with the start symbol, and by applying the production rules, you try to come up with strings comprised of elements from the set of terminal symbols. And any such string you come up with is a string that's recognized by this grammar. So that basically defines, what the language is. And so we looked at a few examples where I gave you particular values for VT, S, and P, and we played around with looking at strings that are produced by that grammar. So that's the analysis component. And that's like Chapter 4 of Engineering 250, where we have a circuit, and we analyze it and figure out what the state diagram looks like for a state machine. The more difficult part is the synthesis task. So for us, that means if we want a grammar which recognizes strings of this type, what should we set VT, S, and P equal to? And just like, synthesis in Engineering 250, just like synthesis in programming or in physics, there's no fixed set of rules for doing this. It's really an experience thing. It takes practice, and the more you work with it, the more you start to understand how to put these grammars together based on what you want the grammar to recognize. So let's start with this and see where this goes. So suppose the language of a particular grammar G is, and I'm going to use some shorthand notation here. I'm going to say 0 to the m, 1 to the n, where m and n are bigger than or equal to 0. Okay, so this shorthand notation, this means repetition. So it means m occurrences of a 0 followed by n occurrences of a 1. And in this case, m and n are bigger than or equal to, let me make them bigger than or equal to 1, just for starting. So what kinds of things would be in here? Well, you've got to have at least 1 0, and you've got to have at least 1 1. But m could be 2, in which case you have 2 zeros and a single 1. Or you could have 2 zeros and 2 1s. Or you could have 3 zeros and a 1. Or you could have 3 zeros and 2 1s. Or you could have, 5 zeros and 7 1s, and so on. So in spoken terms, the language of this grammar would be, any string consisting of at least 1 1 followed by at least 1 0. So any collection of zeros followed by a collection of 1s. As long as you have at least one of each. So that's the language we're after, and we could, try to list all the strings that are part of that language. There's an infinite number of strings. You could have, 5 billion zeros followed by 16 billion and 5 ones. And that's recognized by this grammar. So we start trying to figure out how to describe it as a phrase structure grammar, and mostly this comes down to figuring out production rules. So let me give you an example. So our vocabulary is certainly going to include zeros and ones. Our terminal symbols will be just zeros and ones. Our start symbol we'll just call S, so that's got to be part of our vocabulary. And then our production rules, this is where all the magic happens. So let me show you an example of production rules for this one, and then we'll try a different one and see if you can come up with these. So for example, I'm going to think of the strings as two pieces. I'm going to call this collection of zeros A and this collection of ones B. And I'm going to say my start symbol can be replaced with A followed by B. And now I need to say what A is, and I want to come up with some rules here so that A is going to be a collection of successive zeros. So I'm going to add A and B to my vocabulary. And so here's a trick. We're going to see this a lot. I'm going to say A can be replaced by a 0, or A can be replaced by 0 followed by A. So just looking at these two expressions, what are some of the possible strings that A could be? A could certainly be a 0, which will take care of, that kind of case. But A could also be a 0 followed by an A. Well, since A could be a 0, A could be a 0 followed by another 0, which takes care of, 2 zeros in a row. But if A can be replaced with 2 zeros, I could also say A is a 0 followed by 2 zeros. So A would be transformable into 3 zeros. And these two production rules basically let us replace A with any number of zeros as long as there's at least 1 0. So think about that and ask me questions if that's not clear. And let me do a production tree while we think about that. So A could be a 0 or a 0 followed by an A. And this A could be a 0 or a 0 followed by an A. And this A could be a 0 or a 0 followed by an A, and so on. And so what strings comprise A? Well, there's just a 0. Or there's, a 0 followed by a 0. Or there's a 0 followed by a 0 followed by a 0. That's 3 zeros, and so on. So if we want a string of all zeros, those two rules will do it for us. Alright, so what about B? I want B to look like a string of ones. So what might you guess for production rules to describe B to be one or more ones? And you can use your microphone or you can put this in chat. Yeah. So B could go to a 1, or B could go to a 1B. This rule picks up the case of a single 1. This rule followed by that rule, this is a 1, this B can be replaced by a 1 that picks up two 1s. Or this rule, a 1 followed by a B, where we replace that B with two 1s, that's a string of three 1s. And so this would describe one or more 1s. And we're not going to use stars in here, but that's the right idea. So this is all we need for our set of production rules. And that should completely describe this language. Alright, let me do something slightly different. Suppose I just want a language that recognizes strings of zeros, but I'm actually allowing this string to have no zeros in it. So the empty string would count, a single zero would count, two zeros would count, and so on. This is very related to regexes, so you might have actually been like inspired there when you put the star in, because this notation actually is linked to where the regular expression notation comes from to some degree. So I could have my start symbol go to A, and as usual I could have A go to 0 followed by A. But I'm also going to say A could be replaced by lambda, and lambda is the empty string. I can use that here so that I don't just have, you know, A arrow and then a blank space there. I actually use lambda to say it's being replaced by an empty string. But what does that empty string look like? Well, you don't see it, right? It's a string of length 0. So my string 0, 0, well, this would be a 0 followed by an A. And so, right, so this is 0 followed by A. And the reason that 0 is an A is because it's a 0 followed by an A, where this A is the empty string. So since A can be empty, 0 followed by the empty string, which is just 0, that's something that A can be changed into. And lambda is always the symbol here, so lambda is always an empty string. You don't have to define that. This symbol here is a scribble because I made a mistake. So this looks exactly like the way we defined a string of zeros here, except we allow A to be the empty string instead. And there's multiple ways that you can write these things. For example, I could also say A can be replaced by 0. And that's not incorrect, right? But this case is redundant. Since I know that A could be the empty string, 0A could be just a 0. And so I already have a rule that says A can be changed into 0. So this wouldn't need to be written as a separate rule. But it's not technically incorrect. But it's nice to sort of find like the minimal set of rules that you need. All right, good. So let's do a few more of these. So suppose we want a language which is one or more repetitions of the string 0, 1. So this is shorthand for, m copies of 0, 1, where m's at least 1. So this would include 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, and so on. So our vocabulary is 0, 1 and a start symbol. Our terminals are 0, 1. Our start symbol is S, and we want to define production rules and maybe some more symbols in our vocabulary. So what do you think? What might we use for production rules to make repetitions of 0, 1? Sometimes you might need a lambda even in this case, but for this one you're probably right. You don't need a lambda here. So any thoughts? All right, A goes to 0, 1 or A goes to 0, 1A. Oh, I like it. I like that. So that right there picks up a 0, 1. This picks up a 0, 1 followed by any A, and A could be a 0, 1, so that would pick up this. And if A looks like this would pick up 0, 1 followed by 2 0, 1s, that would pick up that. That looks really good. And I'll just do start symbol goes to A. And I think that's all we need. Yeah, that's an arrow, right? All right, getting the idea? And most of what we're doing in this unit, we're going to have a synthesis part that comes after an analysis part. The analysis part is usually more straightforward. The synthesis is kind of, it's a divergent process. So it takes some getting used to. Why wasn't lambda necessary here? Just because we didn't need it. If we needed to represent an empty string, we could use a lambda. There's no fixed rule for when you need a lambda or not. It's like, do you need the word null in your C program? Well, it really depends what your C program is doing. There's no hard and fast rule I know of, but since this correctly defines this language, then apparently we don't need a lambda. And lambda is just another string we can use. It just happens to be the empty string. And there are a number of different ways we could have written this. Right? This is one way that works. And it kind of depends how you think about the problem. I could have thought of this as a 0 followed by 0 or more repetitions of 1 0 followed by a 1. And I could write a set of production rules that would create that string. Could you just say A goes to AA? The problem with that is, and also A goes to 0, 1, I'm guessing. I don't know if that will get us, yeah, maybe that would. A goes to AA, so this could be a... I think that would work, right? Technically, those production rules, I think, would get you there. So this is a pretty high-level, quick pass over grammars and languages. In a full course on automata theory, I'll talk about different types of grammars, and there's a whole hierarchy of classification that deals with certain characteristics. And this has a different characteristic from this, for example. One thing that's different about this is that if you were to try to look at a string, so suppose I have a string 0, 1, you know, ha 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 ha, you know, something that laughs at you forever. So I could say A is a 0, 1, well, I've got more stuff in that. I could say A is just an A followed by an A. I have no way of knowing if this is an A followed by an A, right? If I try to diagram this sentence using this rule, I could say, well, this is an A. What about this? Is this an A? Well, I don't know. It could be an A if this is an A and that's an A. So maybe this is an A. And maybe this is also an A. Is this an A? Well, it could be an A followed by an A. I don't know if it is or isn't. And we're thinking about we're thinking about writing computer code that processes this. And for technical reasons that we'll sort of see later on, right? It's easier for a computer to deal with this if there's some if there's some terminal symbol in these expressions, or if we follow these expressions, if we eventually get to a terminal symbol. And this basically says, you know, A could be an AA, which could be an AAAA, which could be something like this. And we don't have enough information to say this is not what our string looks like. And so implementation-wise, this may be harder for our code to deal with. But as a phrase structure grammar, that's perfectly fine. So that's a subtlety you'll get into in automata theory. All right, so I think you're getting the idea here. Should we do one more of these?
Why not?
Sure. So let's do a 1. That's a scribble. Let's do a 1 followed by a succession of 0 1s followed by a succession of 0s. where n is bigger than or equal to 0, so 0 or more of these, and then at least 1 0 at the end, but any number of zeros. So this would include the string 1 0, 1 0 0, 1 with a bunch of zeros, or also 1 0 1 followed by a 0. Or 1 0 1 followed by a bunch of zeros, or 1 0 1 0 1 followed by zeros, and so on. Or maybe more generally, you know, 1 followed by at least a 0 1, a bunch of 0 1s, and then a bunch of zeros. So all of those strings are part of the language. So let me start a phrase structure grammar. So our vocabulary will have 0, 1. A start symbol, our terminals will be 0, 1. Our start symbol is S. And let's figure out some production rules. So any ideas what direction to go in? Oh, we already got some here. So A goes to 0, 1. So what does S go to? Because this looks promising. So let's start with our start symbol. So 1 is not a recognized string, although 1 0 is. But I'm thinking maybe you've got S going to 1 followed by A followed by B. Right, and I'm kind of taking apart this description of the language like this. And I'm thinking, let's make something A that matches this and make something B that matches this. And I think that's what we've got in chat right now. So this says our start symbol can be a 1 followed by an A and a B. And then A, which can be empty or it can be a collection of 0 1s. So A could be 0 1 followed by A. And since A could also be the empty string, we can let A go to lambda. So it could be no 0 1s, it could be 1 0 1 followed by the empty string, it could be 0 1 followed by 0 1 followed by the empty string. So that's picking up this middle section. And then B could be a 0 or a 0 followed by a B. And that picks up 1 or more repetitions of 0. And so I think that would give you that language. All right. So hopefully you're getting the idea. But this is obviously a little weird, right? This is a pretty straightforward. This is a really straightforward way to describe the elements of a language, and you know, writing that out with some examples is not too hard to do. But going from here to here, very kind of indirect process. Not really sure exactly what the algorithm would be there. Can you use A, B in that before you've defined them? Yeah, so this is a set, so it's unordered. So all of these rules are presented to you at the same time. So that's totally legal. This kind of thing may let us capture things that can't be expressed easily like this, though, or certainly where we can't just list, you know, all the elements in the language, or, you know, some pattern that's easy for somebody to see. This is much more general purpose. But getting to here from here can be tricky, right? So there's other ways we can express languages. And one of these is called Bacchus-Naur form. And these are usually just called BNFs. And BNF is a way to describe a language. And it lends itself pretty nicely to programming. And let me give you an approximate description of what BNF looks like. Mostly we have some sort of expression. We usually put it inside angle brackets. And then we say colon equals equals. And we can list on the right-hand side something that this is replaceable with. So it could be, other things in angle brackets. It could be symbols that, don't get replaced, just like the letter A followed by the letter B. It can include an or symbol to say the expression could be replaced with this or, something else. Or it can include a lambda if we wanted an empty string, or whatever. And so we can describe, what an expression is, and then each of these things, if they're names like this, we could describe those on subsequent lines. So let me give you an example. Let's look at a signed integer. So, in programming languages, collection of digits, possibly starting with a dash in front. And typically not beginning with a 0. So here's the BNF I might write for a signed integer. So a signed int is equal to a sign followed by what I'm going to call a uint, which is an unsigned int. A sign is either a plus or a minus or nothing. So I'm going to allow you to type, positive 12 as an integer, negative 13 as an integer, or just, 25. So the sign could be present or it could be completely missing. An unsigned int I'm going to describe as a non-zero digit followed by a general int. So a general int will be an integer that can start with any digit. A non-zero digit will be something from 1 through 9. So we're not going to let you make a number like 017. All right. So a non-zero digit is a 1 or a 2 or a 3 up through and including a 9. And a general int will be a digit followed by a general int or just an empty string. And a digit can be a non-zero digit or a 0. That is a weird makefile. All right. So unless I messed up here, this would be, a complete description of what we mean by a signed integer. And you can kind of work from the bottom up. So what is a digit? Well, it's either a 1 through 9 or a 0, right? So it's just our usual notion of a single digit. A general integer is any digit followed by a general integer, which will be any digit followed by a general integer, which will be any digit followed by a general integer, or an empty string. So this is 0 or more digits. And my unsigned integer is a non-zero digit, 1 through 9, followed by 0 or more additional digits. So I've got one-digit numbers, or I could have multiple digits. And I haven't limited it to 9 digits here, so these could be like, arbitrarily long, but still finite in length. And then to be a signed int, we need that unsigned integer preceded either by a plus or a minus or by nothing. All right, why do we care about BNF? BNF is a much more natural way to describe the elements of a language. And it's usable by code in pretty straightforward form. So for example, here's the syntax of C in BNF. And this is a little hard to get into because it's so general purpose. But for example, if we jump down in the middle, a conditional expression is a logical or a logical or question mark some expression colon some other expression. And a logical or is a logical and or a logical or followed by two pipes followed by a logical expression. And a logical and is this, and so on. And if you work through this and you write an if statement in C, you could ask if it matches, one of these, and you could work through and diagram it like a sentence and see whether or not it's a valid expression. And this is not all that long, right? It's 4 pages to describe the complete syntax of C. So here's an expression. It's assignment expression or an expression, comma, assignment expression. And what is an assignment expression? Well, it's a conditional expression or unary expression, assignment operator, assignment expression. Here's your operators, here's your unary operators, and so on. Now C does have a simple language compared to some others, but yeah, even so, this is shorter than you might expect. And so a compiler, depending on how it's written, see we got go-tos. Depending on how it's written, a compiler would use some form of this, right? And it may not be parsing BNF, but something equivalent to this, and could take your input and basically say, is this a C program? And I don't actually know where this starts. Translation unit, external declaration. But like function declaration is a good place to start. So when I learned this as an undergrad, I kind of went a little nuts with it. And whatever your favorite tool is, everything starts to look like something you can use that tool for. And so I started writing BNF for like everything. And so I was writing a lot of parsers at the time. And so an expression, for example, is a left expression, some operation in an expression, or a left expression, or a minus sign followed by an expression. This describes most, sort of regular arithmetic expressions that you would write. And a left expression is a variable, a number, or an expression inside parentheses. And then a couple of operators. A variable is an alphabetic character followed by a variable, or an alpha, and a number is a digit followed by a number or a digit. And I don't describe in here what an alpha or a digit is; those are understood. I ported a package from the assembly language of the machine I was working on to C, and it basically lets me describe this BNF as a series of C statements. So I'm defining something called parse, and it looks for an expression. And if it finds that expression, it looks for the end of the string. And so that's telling me if my input string is an expression. And an expression is a minus sign, right? And if I find a minus sign, I go down here to S4, followed by an expression. That indicates success. Or it could be a left expression, followed by whatever is at S5, which is an operator, followed by whatever is at S6, which is an expression. So that's a left expression, operator, expression. And so this series of statements basically codes this BNF. And it's completely mechanical, right? Once you know this language, to go from a BNF to this collection of gibberish, right? Which basically codes it. And yeah, these are defines, right? So this is all a macro package. And these things are C macros, and then end state marks the end of it. And now to parse my input, right? All you got to do is say parse buffer and see if it returns a 1 or a 0. And if it returns a 0, there's this variable max string which tells me how far it got into the parsing before it encountered a problem. So if I run this, I can say something like, you know, a plus 2 times b, and it'll be perfectly happy with that. If I do a plus 2 times plus b, it'll complain that there's something wrong right around the asterisk. Right? It found an extra operator after that. Right, if I do that, it's missing a parentheses at the end, and it knows it. And if I put an extra paren on the end, it'll come back and be happy with that. And what's cool about this is that while you're doing this parsing, you can actually be interpreting the code, not just checking its syntax to see if it's correct or not. But for example, every time I have an expression inside parentheses, I know I need to evaluate that expression and then use that value. If that was, you know, an expression right here, I know I need to evaluate the left expression and the expression and then apply that operation. And so this is part of how you write a compiler, right? It's not just checking the syntax, but it's actually going to generate code that will do what your statements say. So if you say something like x equals, you know, b plus c, something like this can help you generate code which says take b, take c, add them together, store the result in x. So you can take a whole class on compiler design. I took one in my graduate program. This is, again, just kind of a very high-level pass over a number of topics related to this. But this is a little bit of how you start with this. And there's, you know, a lot of this that can be mechanized. So there's a standard piece of Unix called Lex. It's a lexical analyzer. And you can use that to write compilers, right? And there's another tool called Yak. And Yak is yet another compiler. So it's a tool that basically you make a description of what you want your compiler to do, and you run it through Yak, and it makes a compiler for you. And then you can feed programs into that compiler and compile them into some other language. And so a lot of this stuff is mechanized, right? A lot of this stuff has been bundled and is available as tools in Unix. So Lex and Yak are a classic pair. There's actually a O'Reilly book called Lex and Yak that just talks about those two. Yeah, compleception. Exactly. All right. So all of this is closely related to finite state machines. And the code that I was showing you, that was basically implementing a finite state machine. And as you move through the BNF and you match certain parts of it, you basically change from state to state. And so you might start off in a state where you're looking for a signed int, and if you find a sign, then you might go to a state where you're looking for an unsigned int. And you might find a non-zero digit and then go to a state where you're looking for a general int. So let's talk about finite state machines. And I promised you we won't be doing anything with flip-flops or really wide state tables. So we'll do this from a more theoretical point of view. So what is a finite state machine? It's basically a set of tuples. So the tuples basically list present state, input, output, and next state. And I know that's where we start from in 250. So at any moment, the machine has some notion of state, right? What state is it in? And you can just think of it as, you know, an integer, if you like. I'm in state 1, I'm in state 7. But the state somehow records some information about where the machine's been, what it's seen in the past. So you have a current state or a present state. You have some piece of input. And based on a table of information, the machine will, in this state with this input, generate some output and change to another state. All right, that's the whole life of a state machine. I'm in this state, I see some input, okay, I'm going to generate this output, I'm going to go to this new state. And that's all it does. And if it's a clocked system, a synchronous machine, which is usually what we're talking about, then every time a clock ticks, it looks at its current state and its input. Based on this table, state diagram, right, it comes up with an output and decides what its next state is going to be. Next time the clock ticks, it goes into the next state and it repeats that. So yeah, pretty boring life. That's the nature of being a computer. And computers are basically state machines, right? And we can think of lots of things in terms of state machines. And so one example that I use when I teach 250 of a state machine would be something like this. So each of these represents a state, and usually we draw arrows, and these arrows have a number associated with them corresponding to an input. And we usually have a key which says state, and we list our input on here. And so this is going to be a state machine for weather prediction. And so this state is going to be definitely rainy. This is rainy, this is sunny, and this is definitely sunny. And our input is going to be 1 if it's sunny, and 0 if it's not sunny. And this machine ticks once per day. I know, that was a cool T-storm. This machine ticks once per day, and here's the idea. Suppose that right now, you know, it's like totally rainy, right? Just use your imagination, pretend it rains around here. So it's totally rainy. Oh, I missed some states. So this is a 0. This is a 0. 1, 0, 1. This is a 1. All right. So suppose it's raining right now, and suppose it's not sunny, right? We can probably predict it's going to be rainy tomorrow. But suppose it's rainy today, but then at some point the sun comes out, right? So end of the day, it's not raining. Since our input is a 1 because it's sunny, we're going to change our prediction for tomorrow's weather to say, yeah, it's probably going to rain tomorrow, but we're not quite as definite. And if it rains tomorrow, right, if it's not sunny, we're going to go back here and we're going to say, yeah, tomorrow it's going to definitely rain. But suppose, the sun comes out today, and so we predict tomorrow is probably going to rain, but guess what? Tomorrow turns out to be a sunny day. So we've had 2 sunny days in a row, so now we're going to predict tomorrow is going to be sunny also. And we're not positive, but we're thinking it's probably going to be sunny. If it turns out to be sunny tomorrow also, now we end up in this definitely sunny state. And if it's sunny today, we're going to predict, yeah, tomorrow's definitely sunny. And the whole idea is, right, if it's sunny for a few days in a row, it's probably a streak. And if it's rainy for a few days in a row, it's probably a streak. And so this is making its prediction based on what's happened in the past. If it's been sunny for a few days and it's sunny once more, we're going to say, yeah, it's definitely going to be sunny tomorrow. But if it's been raining for a day and then we had 1 sunny day and it's sunny today, we're going to say it's probably sunny, but we're not quite definite yet. And if it's not quite definite and it turns out to rain, we're going to go back to predicting rain. But if it's been sunny for a week and we get 1 rainy day, we're going to come back here, we're going to say, yeah, I think it's probably going to be sunny tomorrow. Right? So that's the notion of state. And these are 4 different states that our predictor could be in. 0.6 miles, wow, that is close. That was probably really loud. Yeah. Yeah, we don't get a lot of thunderstorms out here. Back east, it was pretty common. But it's still pretty shocking when it's that close, no pun intended.
Yeah, I'm just working on homework and then boom, there it was.
I remember as a kid, I was in my room and I was playing violin, and there was this huge crack of lightning, of thunder, and I looked outside and the tree was falling, like right in front of my house, this big old tree, and it just gotten smacked by lightning. It's pretty impressive. All right, this, by the way, this weather predictor is actually inside most modern CPUs. This also works for branch prediction. And basically, when you're coming to a conditional branch, your computer tries to predict ahead of time whether you're going to take that branch or not. This has to do with trying to get high performance out of a CPU. And we have these instruction pipelines. If you've done 270, you know about instruction pipelines. You can keep the pipeline full if you correctly guess whether or not a future branch is going to be taken. So there's a little circuit like this, a little state machine, which tries to predict whether a branch is going to happen. And basically, if you've taken a branch at the last time that you came to this location, you're probably going to take that branch the next time. If you branch 2 times in a row, you're almost certainly going to branch the next time you get there. And if you don't branch the last 2 times that you came to this instruction, you're probably not going to branch the next time. And so this is actually a state machine for what's called a 2-bit branch predictor. And that's part of the key to keeping modern processors running quickly. Upstate New York, awesome. Oh, Missouri too, yeah. Yeah, tornadoes are interesting. I encountered those when I moved to North Carolina. I grew up in downstate New York, so we always had good thunderstorms in summertime. All right, let's see, where are we here? I'm not going to go into a lot more detail on state machines. I know that people work with state machines in Engineering 250, and so I'm not going to dig into that. I'm going to go into some other particular types of state machines. So let's talk about Turing machines. Well, we never did get to DES, to RSA this quarter, did we? Maybe we'll try to squeeze that in on Friday. Oh, that's memorable though. No, Turing machines don't really lead to crypto, although Turing machines kind of, they're related to crypto historically. All right, Turing machine. So does everybody know who Alan Turing was? Is that name familiar? Cool. All right, so Alan Turing, right, mathematician mainly, although a lot of other things, um, and he was interested in the theory of computation. So this is back in like the 20s, right, the other 20s, um, and trying to understand what it means to be able to solve a problem. Well, if you can describe an algorithm to describe to solve a problem, right, then maybe we can automate that. But what is an algorithm? So, imitation game. So, in order to study algorithms, we needed a theoretical model of computation, right? Of following an algorithm, and a Turing machine was designed more or less as a theoretical version of how we might, follow some step by step procedure. And so we can think of this as a physical machine, and there's a magnetic tape or a paper tape or something, and the tape is infinitely long. Okay, so limitless supply, and there's some kind of read-write head sitting here, and there are spaces on this tape, and each space can contain a symbol. And the set of symbols is up to you. Sometimes it's just a 0 or a 1. Sometimes it's other characters. And so you can have symbols on here, and there's this read-write head, which can do two things. It can read a symbol that's directly in front of it, and it can also write a symbol in that spot. And the Turing machine has a sense of state, so it knows, what kind of state it's in. And we have a big table of state transitions, and these basically look like this. If you're in a present state, and you see a particular symbol, so this is the current symbol, then you should write a new symbol, and you should move left or right, move the tape left or right, and then you should go to some new state. So it's a set of these 5 tuples. Yeah, that's a good chat going on here. Turing machines were, and Alan Turing in particular, was instrumental in England in helping to crack the Germans' Enigma crypto system, which undoubtedly helped the war effort come out the way it did. And it's a really sad story. Alan Turing's life. He was eventually ostracized for his sexual preferences, and his life was basically ruined because of these silly social norms, as they call them. And I think the government finally apologized, several years ago, coming up on the 100th anniversary of all of this stuff. I think they issued a formal apology for the treatment of Alan Turing. But he was a genius, right? I mean, everything that we do today with computers is basically happening on a Turing machine. So this all really kind of came from these beginnings. All right, so we can write programs by simply listing a table of present state, current symbol, new symbol, direction to move in, and what the next state should be. And it turns out that by doing this, we can do computation. And so let's do some examples. So suppose our tape contains the following examples. So this is an infinite tape, but I'm not going to draw an infinite tape on paper. So suppose our tape contains, you know, like and I'm just going to list dashes for blanks. And I'm going to suppose that this tape contains, you know, no characters anywhere over here, and it contains 3 ones and 2 zeros. And I'm going to draw an arrow for my read-write head. And normally the tape would be moving, but I'm just going to move the arrow around because it's easier to scratch out and replace where this thing is rather than redrawing my tape. So, let's write some state transitions. So I'm going to do the following. I'm making this up as I go. So state 1, and I'm going to use this for a blank, so a B with a slash through it. All right. So here's a Turing machine with 3 transitions listed in the state table. And we're going to assume that our initial state is S1. So just like a 250 state machine, you got to know what state you're starting in. So we're starting in state 1. And here's what this machine would do. So this is the read-write head. It's sitting right here on top of a 1. It's going to look at all of the things in its state transition table. It's going to find, hopefully, one of these things that applies. Okay? And if it finds, you know, that this is the state it's in and this is what's under the read-write head, then it will go ahead and write this character and move in this direction and go to this state. If at any point it does not find an entry that matches its current state and input, then the machine halts. It's done. Okay? So what's it going to do right here? It's sitting right here. It sits at state 1. It's looking for a 1. So if you're in state 1 and there's a blank underneath you, well, that doesn't apply. If you're in state 1 and there's a 1, that does apply. So what should it do? It should write a 1, which we'll leave this as a 1. It should move to the left. So now it's going to sit right here, and it should go back to state 1. Okay, so now we're sitting here, we're in state 1, and there's a 1. Same thing. Start at the beginning, find a rule that matches. State 1 blank, no. State 1, 1, yes. So what should it do? Write a 1, move to the left, change to state 1. Okay, back to the top. If you're in state 1 and there's a blank, leave a blank, go to the left, state 1. It's not a blank under there, it's a 1. So state 1 and a 1, that's what matches. So we're going to write a 1, we're going to move to the left, and then it's going to go to state 1. Okay, state 1 and a blank, no. State 1 and a 1, no. State 1 and a 0, that matches our current condition. So it's going to write a 0, it's going to move to the left, and it's going to go to state 9. So it's in state 9 and there's a 0, it's going to look, there's no rule for a state 9, the system will halt, and it's done. So what did this program just do? It basically moved left until it found the first 0, and then it moved 1 spot to the left of that, and it finished. Okay, maybe not the most useful program in the world, but that's what that particular 3-state program does. And if you had started over here, well, then this first statement would have said if you're in state 1 and there's a blank, leave the blank there and move to the left, go to state 1. So this would start skipping over the blanks until it got to a 1, and this is skipping over the 1s, and then when you get to a 0, you move 1 spot to the left and you go to state 9. So let me show you a more useful program. Let me see if I can get this right. Is that all we need? All right, so suppose this is our string and we're starting right there. And we're starting in S0. That's our initial state. So if you're in state 0 and there's a 0, we're going to leave that as a 0. We're going to move left, and we're going to stay in state 0. So now we're in state 0, there's a 0, we're going to leave that as a 0. We're going to move left and stay in state 0. Now we're in state 0 and there's a 1. We're going to leave that as a 1. We're going to move left, but we're going to go to state S1. So S1, there's a 1. We're going to replace that with a 0. Let me record what our original string was. We're going to replace that with a 0. We're going to move left and stay in state S1. S1 and a 0, we're going to replace that with a 1. We're going to move left and stay in state 1. S1 and a 0, we're going to replace that with a 1. Move left and stay in state 1. Now we're in state 1 and there's a blank. There's no state description that matches state 1 with a blank, and so our system halts. And our input was this, and now our new string looks like this. So what is the meaning of this output compared to this input? Anybody recognize this? Think Engineering 250. Yep, that's the 2's complement of that. If you take your input and you complement every bit and you add 1, you get 110, 100. That's the 2's complement. So this Turing machine program takes a binary number and converts it into the negative value of that binary number using 2's complement. If that was a guess, that was an excellent guess. Yeah, so we can do, useful things with Turing machines. And that's not surprising because Turing machines are, the basis for our machines today. And so let me see if I can find something here. So there's a bunch of these available, but here's a Turing machine simulator. And this Turing machine lets you put in comments, which is like bonus, right? Get your extra points on the grading rubric. And it's got some other niceties. It's got wildcards and stuff like that. But this is basically the same type of Turing machine. And you can load a program in here. You can load an initial value into the tape. There's the read-write head. And you can step this and see what it does. So you can see which instructions are executing. And how the tape is being modified. And so on and so forth. And so that program turns our string into a smiley face. Alright, so this is checking to see if an input string is a palindrome. So here, the input string left and right sides were symmetric. If I throw an extra 1 in the beginning, and I run that, right, I get the sad face because it's not a palindrome. So here's your 121 palindrome program written as a Turing machine. And there's lots of sample code in here. So here's binary addition, and this is a little bit longer, but not too bad. So somebody give me 2 numbers, reasonably small enough that I can convert to binary. Okay, so 12 and I'm guessing that's 9, not 1001. So let's do 12 and 9. So 1100 and 1001. And let's load those onto our tape. And let's add them together. So what is 12 plus 9? That should be 21. We should be 16, 4, and 1. So let's run this and see what it does. And there you go, 16, 4, and 1. And our machine halted. That's okay, binary's cool. And you can see it took 69 steps to do that, so that's not too bad. So let's look at some more interesting examples. Let's do a multiplication. So let's do the same one. Let's do 12. Let's do 12 times 3. Because that's 36. That's a pretty easy one to convert. So 12 times 3. And let's run that. And you know, just like our phrase structure grammars, it's using temporary variables, so I, O, X, to keep track of where it is. The tape is the input and the output, but it's also the memory, right? And the program is stored somewhere else. The program is, you know, something that the machine has access to. It's not actually stored on the tape. So there you go, 32 and 4 is 36. That's 12 times 3. All right, so let's look at my favorite primality test. So let's check to see if something's prime. So let's check the number 5, and we'll run that. And I'm going to click this Run at Full Speed button. And 5 is a prime number, and that took almost 1,600 steps. Alright, so let's try 31. And let's run that. And this will go for a while. And this is, you know, a pretty long program. So it's you know, 200 some statements. And this is kind of like, you know, you can write a program in C, and if you convert that into assembly language by compiling it, it may be a lot longer than your original C program. Well, this is lower level than assembly language, right? This is closer to what goes on inside a CPU when it executes machine code. So the programs are pretty long, and they do a lot of work, right? But this might be, you know, kind of analogous to clock cycles. And you look at your C code and you say, yeah, I'm going to go through this loop 20 times, but how many clock ticks does that correspond to? Well, it could be quite a bit more. And, you know, there's nothing on a Turing machine inherently that does division or modulos. You have to write code for that. And so somewhere in here is a divide algorithm. And there might be enough comments, so they might be dividing by just successively subtracting. But all this has to get spelled out. Yeah, there are languages lower level than assembly language. All right, there we go. It's prime 45,000 steps later. And if we try 30, I think it will probably find that's not prime pretty quickly, because that's divisible by 2. Oh, there's 10,000 steps. Now, a funny thing about Turing machines is, you know, you start off by analyzing them, right? And then you start trying to write some. And after a while, you start to really see how to think in these terms. So that was less than half as many steps, 18,000 to find a factor. So I'm running at full speed, so I don't know, that was about a minute maybe. So, I don't know, 15,000 steps a minute maybe. 1,506 seconds, so a few thousand a second. Yes, definitely. And you know, it's updating the graphics and stuff like that. You could certainly make a faster Turing machine. but you know, it's a lot of operations. But you can learn, you know, little tricks to figure out how to write code, just like we learn tricks to write C programs, right? I mean, the first time you try to write a C program, you have no idea what to do. Probably you've got, you know, a bunch of things you can choose from, and should I do an if? Should I do a for? You know, who knows? But with practice and, you know, trial and error, eventually we're able to write a C program. And then we get to 270 and we've got pick assembly language. No idea what to do. You know, should I do a comma A here? Should I do an increment? Should I do one of those conditional things that skips, you know? But after you do enough of these, right, you start to see patterns. Oh, if I want to, you know, check to see if something is 0 and do this, well, I'll do a move F and I'll do a test and skip if 0. And then in the next one, I'll say where to branch to. And, you know, we figure these things out. And it's the same thing with Turing machines. And there are other languages that make this look like, you know, Python or Java, something high powered. There's these esoteric languages that have, you know, a few symbols to them. There's a language based entirely on white space. There's a 0-bit language that I've been researching for a few years now. There's Rockstar, which is a really cool programming language. If you haven't checked it out, check it out. So lots of different ways to code up algorithms. Turing machines are interesting because, you know, they're a simple definition. They're universally complete. We can write any program on a Turing machine that we can write on a Pentium processor, for example. But they lend themselves well to theoretical analysis. When you have a new language or a new processor or something like that, and you want to know, is this universal enough to write basically anything that I would want to write? The terminology is it Turing complete? The benchmark is this good enough to do anything I can do on a Turing machine? So this is sort of, you know, the gold standard of, you know, okay, here's a new language called Ruby. Is Ruby powerful enough to do anything I could do on a Turing machine? If it is, then it's called Turing complete. And it's, you know, a viable programming language. So even though this is, you know, pretty rudimentary, this is kind of what we mean by a universal language. All right, so we are just about out of time for today. So Wednesday, I want to talk about a different type of Turing machine. And this is something called a non-deterministic Turing machine. And this is a Turing machine with a special component inside which we call a genie. Okay, and a genie is able to predict the future and has, you know, omniscient knowledge of everything and can help you solve computations more quickly. And we're going to look at what kinds of things we can do with a non-deterministic Turing machine. And this is going to lead us to a brief discussion of classes of algorithms and algorithms that can be solved in certain bounds of time. And so we'll talk about that. That will lead us to something about PNP completeness. And we'll talk about something called the halting problem, and that will probably round out our discussion for 215. And then Friday I'm just going to leave for review and picking up any topics that we haven't covered that we want to talk about. Cool. So have a good afternoon. I will see you next time.